So we'll go ahead and get started. I'm sorry about the technical difficulties at the beginning. I changed the some of the settings for, I have a meeting later today for Link Crew, and I guess I didn't realize that it applies to all meetings, so my bad with that. But this is lesson number 39. We're finishing up polar equations today. This is probably our, I want to say, like 80th or 90th lesson of the year. So we've done a lot of lessons, and this one will be the last one. So I was typing the message last night, and I was kind of getting sad. I was like, wow, this is the last lesson with my fast track kids. So I was kind of sad about that. But here's what today will look like, and then the next couple of weeks. So today we're doing graphing polar equations. So that's just a continuation of yesterday. Zoom office hours, I'm not going to have that tomorrow just because in the past few weeks I haven't seen it to be necessary. Y'all send me your questions via Remind, and that's been sufficient, and not a lot of people have been joining the Zoom office hour. So if you have any questions, you can just continue to shoot me a message on Remind, and I'll answer any questions you have about any of the practices. But all the practices will be due tomorrow for this week. Remember, it's only 6 grades, and so right now there's 4 in the grade book. So I'll grade 1 more for this week. I'll pick something at random, and then and you have a 6th grade, and that grade will be a survey. So in the next 2 weeks, your only required thing that you'll do, I really want y'all to focus on your AP exams, because I know some of y'all have multiple, and so we won't have a class the next 2 weeks. I want you to just focus on that, studying for those and preparing. And so we won't have a class. It would just be, I'll send out a kind of practice that will have some of the topics that you'll be using immediately in calculus, things like the unit circle, things like trig graphs, things like rational functions, all other kind of some of the things that you will be using immediately in the first 6 weeks of calculus, just kind of like a review. I'll send that out via Google Classroom sometime next week, and you can use that in practice, and I'll probably upload the answers as well. So you can use that to help you prepare for calculus. Maybe just like a couple sheet just to highlight a few things. Keep your binder, obviously, that will help you as well. And then I'll send out a survey, and the survey will just be, I do it at the end of every year, just how the class has been. I always want to improve as a teacher, and so it's just, what are your reflections in the class? What went well? What didn't go so well? What could be improved in future years for my future kids? So if you can answer that survey will be your 6th grade. It will be a completion grade. You fill out the survey 100. You don't fill out the survey 0. So that's kind of a freebie grade there. And then after that, ACP testing, but we don't have ACP testing. So really, we're kind of going to be finishing up the school year a little bit early there. And in terms of my class, I'm not going to do anything those days. I'm not sure what your other teachers are doing. So so this will be the last formal lesson, and the next 2 weeks will be that. So any questions with respect to that, or to the calendar or anything like that? Might be slightly different from your other classes, but any questions with respect to any of that? Yes. Oh, yes. Thank you. What do we do with the books, right? Because y'all have, I think some of y'all have Algebra 2 and Pre-Cal books, right?
Yeah.
Thank you for reminding me. I meant to make a note of that. So just next school year, when y'all come back, I know it's big books and they might take up space in your room, but maybe put it under your bed or something. Yeah. So if you can bring it back next school year, just stop by my room and drop them off. In addition to calculators, some of y'all had borrowed the old calculators, and you didn't know that we wouldn't be returning, obviously. So a few of y'all still have that. I think I have a list somewhere in my desk. So if you have a book, or if you have a textbook, or you have a calculator, you can drop that off next school year when we come back, whenever that is. So, okay. Good question. Thank you for making a note of that. Any other questions? Okay. Well, we will go ahead and get started. The 4 goals has been a big part of my class, and we spent a lot of time watching different videos, doing different activities to kind of talk about the importance of learning math, building character, not giving up, and asking why. And my hope is that it has been an encouragement to you, that it has been kind of part of our culture, our class, but has been motivated in some form or fashion for you, because that's kind of what my class is all centered around. My goal is at the end of the year that students reflecting on the year would feel like they have learn math and learn math well in my classroom. Math for a lot of students is kind of a sore subject, and maybe not so much for y'all because you're in fast track, but my hope is that wherever a student is, that they feel like they learn. And then secondly, feel like they not just improve intellectually, but improve as a person in their character, and just want to encourage positive character traits, working together, things of that nature. Thirdly, not giving up in the face of obstacles that life throws at you, which is inevitable, and challenges that math has when you get frustrated with the problem. Y'all know my, not having a jelly bean in my class is kind of a funny thing, but it's kind of to break that habit of saying I give up. And then lastly, to understand the why behind the math and truly understand the depth of it and not just the steps, and also to feel comfortable asking questions, because asking is how you learn. My hope is that you've done those 4 things. We say them at the beginning of every class really as a reminder, but that is at the core of what I want to do as an educator and what I want my kids to experience in my classroom. So I want everybody to unmute themselves for a moment, and we'll say the 4 goals together for the last time here. So give me a second there. All right, so we'll say it together. We will
Will
learn math,
learn math,
build character,
build character,
never give up,
Never give up.
give up,
ask why.
Ask
why.
why.
Awesome.
Mr. T, you muted yourself.
Oh, I did? Oh, my bad. Did y'all hear what I said?
No.
Oh, I said it's a little bit different in person versus over the computer. I heard y'all saying it like 5 different iterations of each one. It was just funny. Okay, so here's what we're looking at today. This is the graphing polar equation. So what we did last class was we looked at what is a polar coordinate system, how do you plot points on that polar coordinate system, and today we're looking at equations. So if you think about just from a rectangular perspective, when you had a point in the x and y axis, it was just a point, right? But then we look at the relationship between y and x, then you form graphs like lines or quadratics or different functions. It's the same thing with polar, but polar kind of creates these cool, neat graphs that look like these shapes like roses and different curves and things like that when you look at the relationship between r and theta, okay? R, because remember, instead of x comma y, it's r comma theta. So when you set it up in an equation of a relationship and between r equals and then some equation and theta, you kind of create these cool, neat looking graphs. So that's what we're looking at today. Where did those come from, okay? So let's start with first just a basic. Let's just say we had r equals 4, okay? Remember, r is referring to the distance from the pole to the point. And so if we're saying r equals 4 for all of the points, then if you think about it, here's r equals 4 right here. That is true for for that point, because this would be 4 comma 0, 0 being the angle of 0. This point right here would be 4 comma pi over 6, right? And r is 4. So r could be 4 anywhere where the distance from the pole to the point is 4. And so really there's an infinite amount of values, right? So these two are, this one is 4, this one the distance is 4, this one is 4. So we're gonna have all of these points that are 4. So what this would create is just a simple circle, r equals 4, because all of these points have a r of 4, okay? So when it's r equals in a value, it's going to create a circle because those are all the points in which r is 4. If it's r equals 2, then that would be right here is the r of 2 anywhere along this path. Okay. And then if we have theta equals pi over 4, then we're looking at where the angle is pi over 4, which is 45 degrees. And that would be right here. That's an angle of pi over 4, right? Now, it doesn't specify what the r is. So the r could be 1, and then you would have a point here. The r could be 2, and you can have a point here. The r would be 3, you would have a point here. The r would be 4, you have a point there. So anywhere along there, the angle is pi over 4. So this would create a line. All of these have an angle of pi over 4. You can also have a r that's negative, which would extend in the opposite direction. So if the r is negative, you would have all these over here as well. So if its angle equals pi over 4, you would create a line. These would be kind of simple examples of a polar coordinate plane, how you would form different shapes from just r equals and theta equals. Any questions thus far? Good. Okay. All right. So let's look at circles. When you start to add cosine and sine into the equation, it starts to do some different things. So looking at this first example here, I think in your notes it's printed, right? Yeah, I had it printed. So if you have r equals, now if you don't have r equals 4, but let's say we say r equals 4 cosine of theta, then it creates this circle, okay? If you say r equals -6 cosine of theta, is going to create this circle, okay? So let's just stick with cosine first. Let's just look at those two. If we think about the a, okay, so the general form of this equation we're saying is r equals a times cosine of theta. R equals a times cosine of theta. So if you think about the a of the first one is 4. This is our a, right? So the a of the first one is 4. The a of the second one is -6. What do you think, looking at the graph, what do you think the a might represent? Of the circle.
The diameter?
Yep, a is going to be the diameter, because here the distance is 4. Here the distance is 6, so we're going to have to take the absolute value of -6, which would be 6, right? So a is going to be always the diameter if it's in this form. Okay. And then when a is positive, like in this first case here, then it's going to be shifted to the right. When a is negative, like in this case here, is going to be shifted to the left. Okay. That's creating a circle. Whenever you have r equals a times cosine of theta, and you graph that in the polar, it's going to create a circle there. Okay. Now let's say you have sine. So let's say you have it in the form r equals a times sine of theta. That would also create a circle. So in this case, our a is 2. In this case, our a is -3. However, if you notice, the circle is just in a different place. A is still representing the diameter, because this diameter is 2. This one diameter, the diameter is 3. So a was going to tell you the diameter. And when a is positive, if it's sine, then it's shifted up from the pole. If a is negative, it's going to be shifted down. Okay. So whenever you have the equation r equals a times cosine of theta, or r equals a times sine of theta, then it's going to be a circle, and it's going to be shifted in one or the other ways. Now, the way I remember that is when I think about the unit circle, cosine is x in the unit circle, sine is y in the unit circle. So I think about it as how I remember if it's left or right. If we have a cosine in the circle equation, cosine is x, so it's going to be along the x-axis, either left or right. Sine on the unit circle is y, so that reminds me, okay, if sine is in the equation, it's going to be on the y-axis up or down. That's kind of how I remember those for polar. So that's for circles, and a is just a diameter. Okay. All right. I want to look at this video briefly. It just kind of explains why it is that, like, why does this equation give you a circle? Okay. So we're going to look at that, and then we're going to talk about the rest of the notes, but just a quick explanation. Why does that equation give you a circle? Okay. So let me play this.
rather than in rectangular coordinates. Take the graph of r equals 5. This is a circle with a radius of 5. To convert into rectangular coordinates, we could square both sides and then change r squared into x squared plus y squared. This should look familiar, as it is the form for the equation of a circle that we
Can y'all hear that on your end?
Yeah.
Okay, cool.
already learned, but we can see how it was much easier to interpret in the other form. Therein lies the power of polar coordinates, which wouldn't be very useful for lines unless the line goes through the origin, as these would just be equations with constant angles. But polar coordinates are very useful for things like circles and other shapes. Before we leave this topic, let's talk a little bit about graphing polar equations. Say we have something like r equals 2 cosine theta. One way to plot this is to plug in points. Let's plug in multiples of a 6th pi and see what we get. When theta is 0, cosine is 1 times 2 is 2. So 2, 0 is a point. Plugging in a 6th pi, we get 2 times root 3 over 2, or root 3. We can estimate this to the 10th place and plot that point as well. For a 3rd pi, we get 2 times.
So the sound is a little bit off from the visuals. I'm gonna pause it so you can kind of understand what's going on there. So they plugged in the angle 0. I don't think I can write on this. Oh man, I just rewinded it. So they plug. No. Now I need to go back. I'm sorry.
Rather than in rectangular
Okay, hold
coordinates.
on, I'm gonna start over.
Take the graph of r equals 5.
Let it get to where it was.
This is a circle with a radius of 5. To convert into rectangular coordinates, we could square both sides and then change r squared into x squared plus y squared. This should look familiar, as it is the form for the equation of a circle that we already learned.
So if you note right there, this is connecting, I was talking during this part originally, this is connecting the equation. If you remember, r equals the square root of x squared plus y squared. And r squared therefore would equal x squared plus y squared. I can't write on this to point out what I'm talking about, but if you look there, they changed r squared. So originally r equals 5 was the equation of the circle. That's what we just looked at originally. R equals 5 and polar is a circle. If you square both sides, you'll get r squared equals 25. 5 squared is 25. And r squared can be written as x squared plus y squared. That just converted it into rectangular, because if you think about the equation of a circle is x minus h squared plus y minus k squared plus r squared, r being the radius. So this x squared plus y squared equals 25 is a rectangular form of that circle that we have there.
But we can see how it was much easier to interpret in the other form. Therein lies the power of polar coordinates, which wouldn't be very useful for lines unless the line goes through the origin, as these would just be equations with constant angles. But polar coordinates are very useful for things like circles and other shapes. Before we leave this topic, let's talk a little bit about graphing polar equations. Say we have something like r equals 2 cosine theta. One way to plot this is to plug in points. Let's plug in multiples of a 6th pi and see what we get. When theta is 0, cosine is 1 times 2 is 2. So 2, 0 is a point. Plugging in a 6th pi, we get 2 times root 3 over 2, or root 3. We can estimate this to the 10th place and plot that point as well. For a 3rd pi, we get 2 times 1/2, or 1. And for half pi, we get 0. So we've just constructed a semicircle here. We will find that if we continue through until pi, we get the other half of the.
I'm gonna pause it because his voice is a little bit slower than the video, but basically they plugged in all the values for the angle, right, and got the r, which is the distance from the pole to the point, And then when you continue by plugging in all the points, you end up with the circle there.
Semicircle, and then the values just repeat from there. So this is a circle with a radius of 1, with its center at 1, 0. We can verify this by converting into rectangular form. We just multiply both sides by r, change r squared into x squared plus y squared, and r cosine theta into x. Subtract 2x, and then we can...
Okay, hold on. I wish I could rewind it. It's going a little bit fast. Just want to make sure we're clear on what's going on here. I can't write on it, but just I'm going to go step by step. So you start, this is converting to rectangular. So you start with r equals 2 times cosine of theta, that's in red. And then multiply both sides by r. So you, on the left side, you get r squared. On the right side, you get 2r, because 2 times r is 2r. And then from there, r squared on the left can be converted to x squared plus y squared. And then where's this x squared? Hold on. Where's the 2x right here? Did something erase? Because I see a 2x.
He said that the r cosine of theta would become x.
Okay, gotcha. I was like, that's not here. Okay. Yes, r cosine of theta, okay, is x, because the equation is x equals r times cosine of theta when you're converting from rectangular to polar that we talked about last class, right? So r cosine of theta, thank you, Anna, will change to x. So then you have 2x on the right side. And so x squared plus y squared equals 2x. And then if you subtract 2x to bring it to the other side. And then now what we have is we have the standard form of a circle, and then that's connecting to what we did before. You would now complete the square of this to convert it to standard, or sorry, it's in general form. To convert it to standard form of a circle, you would complete the square. So I think he'll talk about that.
Complete the square with the x terms by adding 1 to both sides, giving us x minus 1 quantity squared plus y squared equals 1, which should be a more familiar version of the equation for this circle. When polar equations get more complicated, their graphs get more complex, producing all kinds of different shapes with loops and rose curves, which can be quite beautiful.
Okay, so I just wanted to kind of preview that because we're just going to look at the equations and the graphs today, not conversions. So just so you can see how that relates and why the graphs are shaped the way that they do. So when you start to get these interesting shapes, all it is by plugging in values into, like, let's say you have this equation here. If you plug in different angle measurements here and you plot those points, you'll get different neat and creative shapes. So that's where what we're about to talk about, because some of the graphs we're about to look at are going to look very interesting. The way they're coming from is by plugging in angles, you get these shapes, okay? So like, for example, that or this curve right here, if you keep plugging in values in here, the r is going to be different and you end up with these shapes, okay? All right, so let's look at rose curves. That is on the, I believe, back page of your notes. That one I didn't print out, so I'm gonna leave this up here for a second, and I'm gonna allow you to copy this down on your notes for a second. I'm gonna zoom in so you can see it better. And the distances, by the way, like, should be the A for this as well. So like this distance should be 4. This distance should be 5. This distance should be 4. And this distance should be 2. So just when you're drawing it, just make sure that you have that as the distances. I'll give you a second to write those down. and maybe send a message in the chat or thumbs up. Okay. So these are going to be called Rose curves. Who said math isn't beautiful? So they're going to be the case when you have r equals. Let me zoom this out for a second. So similar to the equation of a circle, but one slight difference is inside here you're adding a value in front of the theta. That's going to create a Rose curve. If this number was not here, it would be a circle. Okay. So the general form is either r equals a times cosine of n times theta, or r equals a times sine of n times theta. A is going to be similar to how in a circle is the diameter. Here we'll say it's the petal length. A is going to be the petal length, the distance from the pole to the edge of each petal. These are petals here. So from here to here, if the A is 5, then this is 5, the distance, okay? If n is an even number, like in the case of this one and this one, it's even. This is even. This is even. Versus if n is odd, you notice something different. Here, n is an odd number. Here, n is an odd number. What do you notice about the number of petals that you have as compared to whether n is even or whether n is odd? So what do you notice about the number of petals you have as compared to when n is even and when n is odd?
When n is even, you have an even amount of petals.
Okay, so when n is even, you have an even amount of petals because this is even. This one has 8 petals, right?
Mm-hmm.
This one has 4 petals. Okay, what else?
When n is odd, you have an odd number of petals.
Okay, so here we have 3 petals. Here we have 3 petals. What else? So when n is even, you're going to have an even number of petals. When n is odd, you're going to have an odd number of petals. What about the relationship between the exact number of petals you have?
When n is even, it's double the amount of petals.
Okay, good. So when n is even, it's double the amount of petals. So here n was 4, you have 8 petals. Here n was 2, you have 4 petals. So it's 2 times n. So when n is even, you have 2 times n number of petals, okay? And when n is odd?
It's that number of petals.
Yeah, it's going to be that number of petals. So if n is 3, you have 3 petals. So if n is odd, you have n petals. That's always going to be the case. So just by seeing an equation like this, 6, let's say I had this equation. Just by looking at this equation, I know it's a Rose curve. I know that the length of the petal is 3. And we know that's going to have 12 petals because the n is 6. That's an even number. If it's even, you double the amount. It's going to have 12 petals, okay? There's a couple things to know. There's a lot of rules here that we're going to talk about. So I'm going to pause at some point and allow you to reread through all the definitions and stuff and before I ask some check for understanding questions. All right, the difference between cosine and sine here, and this is kind of what I use across the board to help me remember. I think about unit circle, cosine x, sine y. May or may not help you, but that's what I use. So I see these when it's cosine x, so I'm thinking this petal is going to be symmetric to the x-axis. Okay, both of these when it's cosine. So the first petal of cosine is symmetric about the polar axis. All right, I said x-axis, sorry, polar axis, because it's not a rectangular, it's polar. So the first petal of cosine is always symmetric about the polar axis. If it's sine, then the first petal is above the polar axis. That's how I remember kind of how you would graph it. So that's for Rose curves, general kind of features of them, okay? So we have circles, we have Rose curves. Just a quick check for understanding on the circles and the Rose curves. I'm gonna give you a minute to think about these and I'll kind of ask at random the answer to some of these. So take a minute to think about these Okay. First one, Kelly, what is the shape of this called? Kelly, you there? Maybe she stepped out. Brianna, what's the shape of this one called?
Is it a rose curve?
Not quite, because remember the rose curve has to have the value right here.
Oh, it's just circle.
Just a circle. So Tanvi, what's the 5 gonna tell us?
The diameter, and like if it shifted, like how far it shifted.
Okay, so it's gonna tell us the diameter, and in this case, it would be shifted down, left, up, what?
It will be shifted down 5.
Why?
Because it's sine, so it goes down, and it's negative, so it goes up.
Okay, good. So if we were to draw that, we would know, okay, it shifted down, it's a circle. That's not a circle. And 1, 2, 3, 4, 5. That would be kind of a general shape of what it would look like. Okay, what's the shape of this on it?
A rose curve.
Okay, good. And the 2, Kevin, is the what?
The petal length.
Okay. Jimena, and how many petals we got here?
3.
3, yeah, because this is an odd number, so it's going to be the exact value. Good. So that's just kind of general circle rose curves. Let's talk about limicons. Okay. So limicons are going to be kind of like, they look like a heart, I guess you could say, kind of, depending on the values. So let's look at all of these. So the general form of a limicon is going to be R equals A plus or minus B times cosine, or R equals A plus or minus B times sine. So now the difference between these is you have a number plus and then cosine or sine, okay? So in this case, let's just write what our A and our B is. Here our A is 1, our B is 2, here our A is 3, our B is 3, here our A is 4, our B is -2, here our A is 3, our B is 2. Just based on the A and the B, I'm gonna tell you kind of some features of the shape there, okay? So first off, the A plus the B, if you were to add A plus B, if you add these, for example, it'll give you 3. If you add these, it'll give you 6. If you add these, I'm not including the negative there, by the way. I'm doing the absolute value for this. So 4 plus 2, it'll give you 6. If you add these, it'll give you 5. What do we notice that this value, the A plus the B, is for each of these graphs? We should look for that. What is the A plus the B for each of these graphs?
The radius.
Okay. Yes, I know what you mean. We wouldn't technically use the word radius because it's not a circle, but yes, I know what you're saying. The distance from the pole to the edge is what we're saying, like from here to here, right? So yes, distance from the pole to the edge is going to be the case of A plus B. Okay. Oh, it's 4. I need a 4. Now, if A equals B, which is the case here, then it would be called a cardioid. That special type of limicon. And that's going to look like a heart, always. So if A equals B, it will look like a heart. Okay. If A is less than B, which is the case of this first one here, if A is less than B, it will have an inner loop. Told you there's a lot of rules kind of here. So if A is less than B, it will have an inner loop, like this inner loop right here. It's an inner loop. So if A is less than B, it will have an inner loop. If A is equal to B, it will be a cardioid. It will look like a heart. If A is greater than B, which is the case of this one and this one, then it's either going to be convex, which means flat, or we'll have a dimple. This is convex, flat. This is a dimple. If A is greater than B, that would be the case. Those are kind of some of the rules for lemma-con. I'll go through those again. A plus B is the distance from the pole to the edge. That's A plus B. If A equals B, it's a cardioid shaped like a heart. That's this one here. If A is less than B, like this, A is less than B, it's going to have an inner loop. If A is greater than B, like both of these cases, it's going to either be convex or it's going to have a dimple. Okay. Similar rules apply with respect to cosine and sine. If you notice, cosine here lies along the x-axis, cosine along the x-axis, cosine along the x-axis, sine, or not x-axis, polar axis, sorry. Sine is on the vertical polar axis. Okay, so similar to all the other ones. A lot of information in terms of just vocab here, vocabulary. Any questions thus far? Two more shapes. Okay. Lemniscates. This is the next one. So for a lemniscate, by the way, you can graph some of these if you have an Inspire calculator to double check your work. Let me actually see if I can show you that, because that's a kind of a new feature. If you go to this one is different. Okay, graph entry, and then these are polar. So if you go to polar right here, you'll say R equals, and let's say we wanted to type 1 plus 2 cosine of theta. Where's theta on here? Hold on, this is not like my actual calculator. It's on the iPad, so I don't know where the theta is. Theta. Ah, there we go. Okay. And then this is saying from 0 to 2 pi. 2 pi is 6.28. So that's not enough, actually. So I'm going to go back. I'm going to increase this value because you need more than just 0 to 2 pi then. That means to, let's say 0 to 100. Still not enough. That means I need to go negative over here, because in order to graph the whole thing. So I'm just going to say negative 100 to 100. Well, so if you look at that, still not enough. I don't know why that's still not enough. Okay, negative 400, 500. Okay, there we go. So you kind of got to increase the angle, I guess, to get all of it. But so we see here that is the way you can graph it, and that has an inner loop because A is less than B. 1 is smaller than 2. So just to show you that as a feature, okay? So let's go back over here. All right, so a lemniscate, I remember this. Again, if it helps you, use it. If it doesn't, it's fine. As a lemon skating, okay? Work with me. So a lemon, like this right here, like a lemon is shaped like that. And then skating is like moving. So it's like moving over here. So it's a lemon skating, lemon skate. It helps me out. I don't know. You can try it. So that's going to be the case when you have R squared. So you have a square in the R equals A squared and then cosine of 2A or 2 theta or sine. Okay. So A is, you have to take the square root of this. So A will be 5. And A is still going to be the distance from the pole to the edge. Okay. So A is going to be the distance from the pole to the edge. You would have to square root to be sure. So like over here, the A of this first one, you would have to take the square root of that. It would be 4. So the distance from the pole to the edge of that one on the left would be 4. Okay. And notice that the value in here is 2. And that is going to stay as 2. It's not going to change. Okay, so if we wanted to graph the one on the left, it's not graph for us. R squared equals 16 times sine of 2 pi, or 2 theta, sorry. You know that since the A is 4, the distance from the pole to the edge would be 4. Because its sine is going to lie above the axis. So 1, 2, 3, 4. 1, 2, 3. It's going to be kind of something like that, you know. A being this, the 4 would be the distance from the pole to the edge, and then you have lemon skating, and then you have 2 of them, and it's sine, so it's a little bit above the polar axis. So that's kind of it for the lemon escape. Okay. All right. The last one is a spiral of Archimedes. That one's just kind of a spiral. It's pretty straightforward. That's when you have R equals a value times theta. So like here, R equals 3 times theta. It would just give you a spiral. These are some examples. R equals 2 times theta, R equals negative 5 theta, R equals 2 theta plus 4, R equals negative 2 theta plus 3. That will give you a spiral of Archimedes. So those are the 4 different polar equation graphs. So we have circles, rose curves, lemnicons, which have different types, or 5 actually, I'm sorry. Then we have the lemniscates, and we have the spiral of Archimedes. If you look at the notes that was posted, there's additional graphs. Those are the same graphs, it's just more explanation or more examples, I guess, of those. So you just to refer to as notes for you, okay? So let me ask a couple check for understanding questions. And then that's it for this lesson. It's kind of just polar equations. So let me pause and see if there are any questions on any of these that, or let me let you read first. So I'm gonna give you a couple minutes. I received a question on the chat that I want to answer because I didn't clarify that. Thank you for asking that. We had A being greater than 0, A being less than 0, and what is the difference between them? The difference is going to be, if you look at this on the first one, the A is greater than 0. You can see how it starts over here on the right side of the polar axis, and then it goes up. And this one on the right starts kind of on the left side of the polar axis, and it goes down. That's really going to be the only difference between them. Okay, so I'm gonna just ask a few follow-up questions and then have you answer them. So here's some graphs. It's gonna be kind of rapid fire. So I'll just ask a question, call on someone, ask a question, call on someone. So kind of be ready to unmute yourself. First question, what's this called, this shape, Landon?
That's a circle.
Okay, good. Kevin, tell me one feature of this circle that you could, that you know about it, the way it looks.
The 5 is a diameter.
5 is a diameter, good. Second, what's this called, Brianna?
Lemnicon.
Lemnicon, good. What does the A and the B, and which one is bigger and smaller, tell us about the graph, Jimena?
The B is bigger.
Okay, and what does that mean?
It basically means that it is gonna have a loop.
Okay, good. What is this shape right here gonna be, Natalia?
Is it a rose curve?
Yes, it's gonna be a rose curve. Brianna, did I already ask you a question?
Yeah.
Okay. Kelly, then how many petals would that rose curve have?
4.
Good. What is this -3 going to tell us about the rose curve, Maria?
It's gonna tell us that is it the length of the petal?
Length of the petal is going to be 3. Good. What's this shape called, Hugo? Obama. Hugo. Okay. You might be out. Claudia, what's that shape called?
The 3 minus 5 cosine?
Yeah.
It's limacon.
Yes. What's this shape right here going to be, Anna?
A rose curve.
Good. How many petals? Carlos?
5.
Okay. Yeah, 5. All right. Carlos, what's this shape right here going to be? Carlos R, you there? Okay, we'll come back. Maybe he stepped out. Sir Tanvi, what's that shape going to be?
A line.
Line, good. What's this called? And tell me something about it, Brianna.
That's a rose curve. And the 5 is the petal length.
Good. What's this called? And tell me something about it, Kevin.
It's a limacon, and it looks like a heart.
Yes. So therefore, it's a what?
Limacon.
What kind? Has a name, like if it's looks like a heart. When you have a heart attack, it's also
Cardioid.
yeah. It's like a taboo. All right, this one right here. What's this called? And what's something about it, Kelly?
Is it a lemniscate?
No, that has to have R squared. Does start with the L though.
Circle?
Oh, it starts with the L. You said what? It's okay if you're not sure.
Yeah, I'm not sure.
Okay, can someone help her out?
Is it a limacon?
A limacon, yeah, because it has that number A plus a B. And what's one thing about it? Anyone?
The A is 4.
Okay, the A is 4. This one right here, let's go Maria. Well, tell me what's this called and one thing about it.
It's a circle and it's shifted down.
Okay, good. This one right here, what's it called and tell me one thing about it. I didn't call someone. Let's go Landon.
that's lemniscate, and the A is 5 since it's squared.
Good. And lastly, this one right here on a what's it called? R equals 3 theta. That's what it is. Anna. Anna, you there? No. Okay.
I'm not sure.
Oh, okay. Can someone help her out?
Is it the spiral of Archimedes?
Yes, the spiral Archimedes. Yes. Okay. Oh, this was what was on your notes. I'm just trying to find the spiral. Yeah, because it's 3 R equals and then A and then theta. Okay, so this was very good with those. This was on our notes. This is the last part of notes. This is just the same kind of polar equations and graphs. It just shows you a little bit more about them. You can read those on your own time. In closing, why don't we try these 2 last questions? Write your answer in the chat, and we'll talk about them after. So try these 2. This one number 1, this one number 2. So try these and then write your answer in the chat, just to make sure you completely feel comfortable. I see some of y'all's answers. Hugo, I see you on the chat now. I don't know if you maybe stepped out, but earlier I was talking to you. I was asking you something. No worries. Okay, I see a lot of answers on the chat. So for the first one, we should have got D, because our A is 3, so the distance here is 3 petal length. So it can't be A and B because that will have a petal length of 2. And then because the even here, you multiply that times 2, it would be 4 petals, and that has 4 petals. So the first one would be D. Second one, spiral of Archimedes, would be this would be a line. This would be a limicon, because when you move the 2 over, you would subtract 1. This would also be a limicon, and this would be a spiral Archimedes. So D and D. So that's polar equations, okay? Your practice is posted. All your practice is due tomorrow. Yeah, it's basically like a matching activity. So you have, there's a bunch of graphs, and there's a bunch of names, and then characteristics and equations. So you would just write like which graph, like G1, and then there's a name, like is it a limicon? And then what characteristics, there's like C2, there's like different things you would match it with. So you would just submit this paper here, okay? So in closing, just make sure we're cool with next steps. So practices are due tomorrow. Next couple weeks, no class, no Zoom office hours tomorrow. Just want you to focus on AP exams. We have 2 more things I need to grade. In order to have 6 total grades, we can't have more than 6 grades in 6 weeks based on DSD policy. We have 4 right now. One of them will be something we learned this week. One of them will be a survey that I'll send out. to be on the lookout for just class reflection. I don't really know how to close a class online. It's so weird. This year is really a weird year for sure. I don't know how to say goodbye online. It's sad, but hopefully I'll see you later. You know, we'll be back. I just want to say thank you all for being truly an awesome class. I think when I left Samuel, it was hard for me because I had a lot of relationships. Relationships are really the foundation of everything when it comes to really just how I kind of see teaching and see just life really. I just think relationships are foundational, and I don't teach for, I like math, but I don't teach for math, although I enjoy math. I teach for kids and the relationships that are formed over the years. And so I was on the phone with a kid who graduated a few years ago of mine from Samuel. We were just kind of catching up, and it was just really good, but just reminds me of like the impact that kids can have in the future. And yeah, so I really appreciate y'all because when I came from Samuel, it was really hard for me to come to a new school, leaving a school with a bunch of people that I really loved and cared about. And when I moved to Oak Cliff, and I just appreciate y'all for helping my transition to go well in having a new group of kids that I can see as kids that I can say that I love and care about and enjoy teaching. Has helped my transition to be more smooth. I appreciate y'all. Fast Track is my first time teaching Fast Track, and my last time teaching Fast Track, at least for the foreseeable future, because next year it's official. I won't be teaching Fast Track. I'll be teaching Algebra 2 and college and career readiness class. I'll have that as well. Actually, a couple of y'all I might have again. But yeah, so thank y'all for that. I really have enjoyed teaching Fast Track. I'm really proud of the work that y'all have done. The idea of learning 2 math classes in 1 year and never complaining, I really respect that. And I truly did appreciate having y'all first as my first class of the morning. To when I was having a rough day or I didn't get sleep or whatever, you guys truly did bring a smile to my face even when I was not having a good day. And I really enjoyed having y'all first and fifth period, and I will miss that. So thank y'all for being an awesome class. I've told you before, but just to say again, you've been the most intelligent group of kids that I've had in one class of all the classes that I've taught. But more than that, because it's more than just your intelligence, but your character and your camaraderie and how y'all are really respectful and really kind. Truly, I really appreciate and I value that. And so thank y'all for being awesome. I'll continue to be awesome. I can't help you next year. Calculus is not my strength, as y'all know, but you are always welcome to come to my class. You'll actually be right next door because you'll either have Miss Wynn or Miss Jones. So my classroom is always open to my previous students. I'm always available just to talk life, talk school, whatever. My Remind will be closed off soon because it only allows you to have a certain amount of Remind classes, and I need to open one up for next year. But you all have my email address. If you do not, it's Tadesse, TADESSE @DallasISD.org. You can contact me at any time with anything if you just want to update me about life. So I appreciate y'all. It's been truly a pleasure to be y'all's teacher this year. I hope that you've enjoyed the experience, and I hope that you have fulfilled the 4 goals over the course of this year. So I'm gonna miss y'all. Let me log off before I cry. But yeah, thank y'all very much. So I guess those are my closing thoughts. So y'all have been awesome. So thank you.
Thank you, Mr. T.
Yeah.
Thank you. I have 2 questions.
Go for it.
So is this like our last Zoom meeting?
It is, yes.
And so for the next 2 weeks, you're just gonna send like reviews, right?
Next 2 weeks, yeah, I'm gonna send one. What's it called? One survey, and then I'm gonna send one review practice. It just has different problems that we learned over the year that will be some things you'll immediately use.
Okay. And also for the 6th grade like policy thing, does that mean for like every class?
Yes.
Oh, because some of my teachers haven't done that.
They have more than 6 grades or less than 6 grades?
More.
Okay. Give me 1 second. Hold on. Sorry.